Alright, I want to spend some time in this video talking about free body diagrams. Free body diagrams are what we use in physics to represent all the forces that are acting on any body at one particular time. And it may sound complicated, but it's actually pretty simple. By the way, free body diagram is abbreviated FBD. You might want to put that in your notes. To illustrate how to do this, I want to just start out with a fairly simple example. Let's consider that there's an airplane that's flying at a constant speed of 500 miles per hour. It's not going up. It's not going down. It's moving straight horizontally. The first thing I want to do when I consider these situations is I want to just list all of the forces that are going on in that situation, that are acting on that object. And to do that, you can look at that list of forces that's in your notes, on the front page of your notes. So let's consider this one. I know that if an object is on the planet Earth, anywhere within the vicinity of planet Earth, there's going to be a force of gravity, and that's going to be true with 99% of the problems that we do. So we do have gravity working in this example. And we need to stay in the same plane, first of all. And as a side note, just like in the motion problems, in two-dimensional motion, the motion in the x direction didn't affect the motion in the y direction. And that's going to be the same with forces. Forces in the y direction are not going to affect, for the most part, forces in the x direction. There's a few exceptions for that, but for the most part, we're going to stay in the same plane. So gravity in the same plane, in other words, in the y direction, because gravity goes in the y direction. The thing that resists gravity is called the force of lift. Lift that the plane wings produce resists the force of gravity. And if the plane is moving, it must have some sort of thrust force that's causing it to move. Well, not causing it to move, but we can discuss that later. It's keeping it moving, keeping it from slowing down, I guess. And then you also do have some friction on the plane, some air resistance that's acting to oppose the motion. So these are the four forces that I have in this situation, and now I'm going to simply draw a box that represents this object. Okay. Before I go on, I do want to make a couple of notes and make these to yourself, that free body diagrams are only going to include forces. Only forces go on a free body diagram. No velocities, no inertia or mass or acceleration or anything like that. Only forces go on a free body diagram, which is why we specifically label the forces. The other thing that we need to know about a free body diagram is, just by convention, we're going to draw the arrows for these vectors coming out of the box, not going into it. So as I said, I'm going to draw vectors on this diagram to represent the magnitude and direction of each of these forces. So let's start with gravity. I know gravity goes down, and I'm going to put it right here. The next one is the force of lift, in the same direction, in the same plane. The lift force counteracts the force of gravity, and notice that I made these two forces the same length. And I did that on purpose because I specifically said the plane was not moving up or down, it was going horizontally. Keep that in your mind for a little bit later when we talk about what that means. If the plane is moving to the right, it's got to have a thrust force to the right as well. And the force of friction, air resistance, always opposes that motion, so it will be to the left. Again, notice that these two forces have the same magnitude. Their arrows are the same length. That has to be because of what I said about the velocity of the plane, that it's moving at a constant 500 miles per hour. So that's it. So that's my free body diagram for an airplane flying at a constant speed. All right. Let's consider a few more examples. All right. Next, I want to consider an example of, I think on the next one in your notes is the chair, the person sitting in a chair. All right. So you got a person sitting in a chair, forces going on. We have gravity, always, if it's on the planet Earth, and the chair is a surface. All surfaces exert normal forces upward against the objects that are resting on them. So we do have a normal force going on at this point. The chair isn't moving, so I'm not going to have some force that makes it move. I'm not going to have a frictional force either. These are the only two forces that are operating here. So I'll draw my box. Gravity is going to go down. It always goes down. And then the normal force is going to act to resist the force of gravity. So that goes up. And again, if the person is not falling through the chair, these two objects have to be equal in magnitude, or these two forces rather. Let's consider another one. How about the third example? I think there's one with a pig hanging from a ceiling. Pig hanging from a ceiling, just hanging there, not moving. I know we got gravity. Gravity is always working if we're on the planet Earth. And if we're hanging from a ceiling, that assumes that there's an object that is suspending the pig from the ceiling, like a rope or a chain or something like that, which means that there's going to be a tension force going on. And those are the only two forces that are there. Gravity goes down. The tension force is going to act to resist the force of gravity. So there's my tension force. Again, notice that my forces are balanced, equal in magnitude, opposite in direction. Consider a fourth example. Consider that we now have a car that's moving at some constant speed. Doesn't even matter what the speed is. And this is in your notes as well. Forces going on. No, I got gravity. If the car's on a road, the road is a surface. And if the car's not falling through the road, there's got to be a normal force that's keeping that from happening. If the car's moving, you have the force of friction from the road and from the air, but let's just consider the road for now, or perhaps both all together in one. And if it's moving at a constant velocity, it's going to have a thrust force to keep that occurring. So here's my four forces. There's my object, and this one is going to look pretty much almost exactly like the airplane that we had earlier. Gravity, and now instead of lift force, we have a normal force that's resisting the force of gravity. Frictional force goes to the left because the car is moving to the right. And if the car is moving to the right, it's got to have a thrust force that's operating, that's being exerted to the right. Once again, I want you to notice, well, maybe perhaps we should look at all of these diagrams at the same time. The next question on your notes says, are all the forces balanced in each picture? And if you look at all of them, I hope you see that they are. And the only way that you can tell that from looking at the picture is to simply look at the length of the arrows. And if the arrows are the same length in either direction, the forces are balanced. In other words, if this force is the same as this force, that's two equal and opposite forces. Therefore, the forces are balanced, kind of like the situation with the tug of war. Two forces equal in magnitude and going in opposite directions, you get no movement. That's balanced forces. So all these are balanced, we can tell from the pictures. And the next point talks about the net force. Okay, the net force is the same thing as the sum of the forces. And I don't mean that like sum of the forces like the word sum. That's not the truth. The sum means the addition, and it's of all of the forces in one direction. Okay, this is called the net force or the sum force. And if I look at the forces in one direction, for instance, if this gravitational force is a negative 5 newtons, this one would be a positive 5 newtons, down and up. Negative 5 plus a positive 5 gives me a net force of 0. All right, in the next section on your notes, the next question says, if the net force is 0, then the object is not accelerating. So in other words, if the net force is 0, what we say is that those forces are balanced. Those are balanced forces. So that's a balanced situation, and you need to know the term equilibrium. If the net force is zero, if you have the same on one side as you have on the other, we say that that object is in equilibrium. And what equilibrium does not mean is that there is no motion. It does not mean there's no motion. What it does mean is that there is no acceleration. Okay, so all this you need to know. In other words, balanced forces give us no acceleration. The object that has a balanced force could be moving. Again, think about our airplane. This airplane is moving. I hope it is, because if it's not, you don't get a lift force. But I specifically said it was moving at a constant velocity, which means these two forces have to be balanced. Again, go back to Newton's first law. If you do not have an unbalanced outside force, your motion doesn't change. This airplane's motion is not changing because there are no unbalanced outside forces. All right, so if the sum of the forces is zero, the forces are balanced, we have no acceleration, and that object is said to be in equilibrium. However, if the net force is not equal to zero, that object is not in equilibrium, we say that those forces are unbalanced forces. And if the forces are unbalanced, we do get acceleration. Unbalanced forces give us acceleration. Okay, so you need to know about equilibrium, how to recognize a free body diagram for an object that's in equilibrium and what that means. And you need to know that if an object is not in equilibrium, that it is going to be accelerating. Once again, equilibrium means there's no acceleration. It does not mean there's no motion. This object, where the forces are balanced, could be in motion. But what it's not doing is it's not speeding up, it's not slowing down, it's not accelerating. To talk about that more, I want to illustrate this car a little bit better. Look at the car. And I want you to consider, how would this free body diagram change if the car was speeding up? You might want to pause the video for a minute to think about that. And hopefully you've decided at this point that if the car is speeding up, that means the thrust force has to be greater than the frictional force. Speeding up, that means we have acceleration. And if we have acceleration, the forces have to be unbalanced. Therefore, we have to have an unbalanced force in the direction of the acceleration. The car would be speeding up going this direction. You can accelerate the car if we apply a thrust force greater than the frictional force. Now consider that you let your foot off the gas completely and you're coasting and slowing down. What would that free body diagram look like? You might want to pause the video to decide that. Hopefully you recognize that if you let your foot off the gas, what that effectively does is do away with the thrust force. So our new free body diagram would look like this. You'd have gravity still, you'd still have the normal force because you're on the road, but now you only have a force of friction, which is acting to slow you down. Unbalanced forces. We have a force going this way that is unbalanced. There's nothing on the other side balancing it out. Therefore, we get acceleration, change in motion, change in speed. The object is slowing down. Now, one last scenario. Maybe we took our foot off the gas because you passed out or something. I don't know. You passed out, you ran off a cliff. If you run off a cliff, you then become a projectile, right? So think right now, if you run off the cliff and become a projectile, and remember that with a projectile, we neglected the force of friction, which doesn't really matter because friction due to air resistance was not what we considered here. This was the friction from the road. If you leave the road and become a projectile, what does this free body diagram look like? You might want to pause the video now. All right. Hopefully you recognized that if you leave the road, you no longer have a normal force. And if we are neglecting the force of friction due to air resistance and we're not on the road anymore, there's nothing that can give us a frictional force. So that's gone. In other words, the free body diagram for a projectile looks like this. There's your free body diagram for a projectile. Now, let's remember what the definition of a projectile was. A projectile is an object that's going through the air under the influence of only gravity. And that's what this shows. Also remember that we said a projectile in the x direction has constant velocity. And we said it has constant velocity because there's no forces acting in the x direction to cause it to speed up or slow down. And that's what we see here. Again, go back to Newton's first law. If we have no unbalanced outside force, the motion isn't going to change. That's why you have constant velocity in the x direction. And in the y direction, we said that the speed does change. It'll increase in the case of a horizontal projectile. Case of a projectile launched at an angle, it decreases and then increases. The motion changes because of the force of gravity. In other words, this is an unbalanced force. We have an unbalanced outside force. Newton's first law said that unbalanced outside forces cause changes in motion. Changes in motion are acceleration. That's why we have acceleration in the y direction, and we use kinematics and ATVVD to solve for that. So that's how to draw and interpret a free body diagram.